Good afternoon, class. This is statics class, week 5, Monday lecture. Be on chapter 4, force system resultants. And we're going to go through a brief lecture, notes, and then we're going to work some problems out of chapter 4. So I'm going to share the screen. So this is week 5, Monday lecture, chapter 4 on force system resultants. We're going to start learning a little bit about our beams, our structural elements, and something about the way these beams are held in place in terms of supports. This is the beginning. The next, 4 chapters, 4, 5, 6, and 7 form the basis for statics, I think, more so than just about any of the other chapters we're talking about, these next 4 chapters. So let's take a look at force system resultants. First thing I'm going to do is I'm going to construct what's called a cantilever beam. So this is the support system. It could be a plate, many types of situations that can provide this type of support. The beam, I'm going to put a force at the end of this beam at some angle, and let's just call this force F. And we'll locate this some distance x from the support. And what we're going to be talking about is something called static equilibrium. And this is going to be where we're going to learn about free body diagrams also for the first time. So static equilibrium says we have some external forces, or in this case, a force acting on this cantilever beam. And for static equilibrium to exist, there has to be some reaction forces at the support that counteract this force. So that if we sum forces about this support face, the force is equal to 0, and moments are going to be equal to 0 also. Okay, sum of forces 0, sum of moments equal to 0. Okay, let's take a look and see what happens then. We're going to talk about components also. We have briefly, if I have, and this will be given some angle theta, we have a force in the x direction from this force at an angle theta, and there's a force in the y direction. Okay, so we have 2 forces acting at that point. The question is, for this to be in static equilibrium, what must have happen over here at this support? What has to happen at this support? Well, we need to be able to counteract this vertical force, this F sub y. And so over here at this support, we're going to have an F sub y reaction. Okay, it's going to have to be equal to, we'll call this reaction in the y direction, equal to F sub y, so R sub y. And then we have this force in the x direction, which means that we need to have a reaction force equal to f sub x, and that will be our reaction in the x direction. And from now on, what statics is going to be about is finding out what these reaction components are. It's probably the most important thing that we do in statics is being able to determine reactions. There's one other thing happening at this support. This y component of force, this is a cantilever beam, causes this cantilever beam to sort of bend like this. Okay, so it's creating a moment that's causing bending in this beam. Okay, rotation. And that moment is equal to f sub y times x. It's a moment arm. So there has to be, and again, this is going to be in the clockwise direction. Sum of moments equal to 0, which means that there must be a moment created over here, this support, that's equal and opposite in direction to the moment created by this y force. And so the third component of reaction over here is a moment reaction to counteract the moment created by this y component of force. Basically, what we've done is we would have solved for one of the statics problems that we're going to take a look at in the next chapter. So the sum of forces in the x equal to 0. We have this x component. We have this reaction of x. They're going to be equal. Sum of forces in the y equal to 0. We have the y component of force. We have the reaction over here, which is going to be equal to that reaction of this y component of force. So sum of force is equal to 0. And sum of moments equal to 0. We'll just call this m sub r. The moment created by f sub y times x is going to equal to the moment resultant over here in this support condition. This is basically called a fixed, we'll learn this, this is a fixed support. So it says sum of moments equal to 0. So the moment created here is counteracted by the moment developed in this support. This is going to be in a clockwise direction. This is in a counterclockwise direction. Okay, again, plus and minus is equal to 0. So the moment is equal to a force, and we'll see there are other ways we can develop moments, particularly in three-dimensional space, is equal to a force times a perpendicular distance. And the units in our system, UPS is or foot-pounds, or in the SI system would be Newton meters. Okay. This distance, d, is the perpendicular distance. In this case, it's a distance x. It's a perpendicular distance from where you're taking the moment to the force itself. Okay, and usually in most all our problems, we're going to be able to find that perpendicular distance. We may have to do a little bit of calculations, but typically we will be able to do this. Okay. So moment is equal to F times D, the perpendicular distance. We have to have a sign convention, as we do for X and Y forces. To be able to add and subtract, we have a plus force and a negative force in the x direction. We have forces in the y direction, either plus or minus, depending upon where you're at in your axis system. We need to be able to add moments also. To get summation of moments, we have multiple moments created in a system. So the convention is counterclockwise moment is considered positive. A clockwise moment is considered negative. Okay. We have a cross product. Suppose I have two vectors, quantities, force quantities. It's force A, this is force B. I'm going to draw a vector quantity C. And the angle, this will be planar, A and B are in a plane. We'll call this angle theta. So C, these are all vector quantities, is equal to A cross B. We'll call it cross product. And you can write this in scalar form. It's equal to AB sine of theta as scalar quantities. So this is this cross product, and this C is going to be perpendicular to A and B. Okay? So it'll be perpendicular to the plane of A and B. A and B are in this, say, an XY plane. C is going to be perpendicular. So basically it's coming out of the page here. So that is cross product. Now we're going to talk about moments in space. I'm going to draw a three-dimensional axis system. X-axis, Y-axis, and Z-axis. Again, we're just trying to illustrate a three-dimensional space like this. Suppose we have a force in three-dimensional space. Cartesian vector. This is the origin. And what I want is the moment about the origin created by this force F, vector quantity F. And that's equal to R, which is going to be a position vector. And I'll show you this, cross F as a vector quantity. Okay. And again, if it's in three-dimensional space, you can write this in scalar terms as an r sub y f sub x plus r, excuse me, r sub x, r sub x f sub x plus r sub y f sub y plus r sub z f sub z. Okay, so each of these will be different values. You can also write this moment O about the origin and as R1 Fx plus R2 Fy plus R3 Fz. And we'll do some examples. Okay. This position vector from the origin to the force vector. That's what I do. I'm going to create this position vector. I'm going to call this, be different than this one, R1. If I can define this in three-dimensional space, and when we see the problems, we'll be able to define these position vectors in three-dimensional space. This cross product works. That gives us the moment about O. Okay. I can also choose another position vector if I can define it. Call this one R2. R2 cross with F, it's going to give us the same value as R1 cross with F. So this position vector, I can do this. If I can define it, so it's any position vector from the point where you want the moment to be taken to the force itself. Could be any position vector that you can define. It should give you the same value. In other words, if we can define R1 cross F is going to equal R2 cross F is equal to R3 cross F. We're going to choose the position vector where we can define it, and usually it's going to be, well, it could be more than one. A couple of problems could be more than one. The one that's probably the most convenient. We'll try to do that. So the way we're going to write this, the moment about the origin, is going to be a unit vector times this R cross F. And the unit vector is basically related to the XYZ axis system, and we'll show you this in some example problems that we're going to be taking a look at. What we're going to do in these three-dimensional problems is set this up as a matrix, 3 by 3. The unit vector in three-dimensional space is IJK. Okay. In general, it'll be IJK. You know, depending on the problem, and we'll show you some examples. It could be a little bit different. Okay, but basically, we're looking for a moment that's going to be in three-dimensional space, and the unit vector to describe it will be an IJK unit vector. The R will be R sub x, R sub y, and R sub z. So that'll be the position vector in the X, Y, and Z direction dimensions on that position vector. The third row is the three components of that Cartesian vector, f sub x, f sub y, and f sub z. So this is the moment, about some point, in this case, the origin will do this in general, is the r cross f. So it's vectors. Okay. The IJK represents the three-dimensional system that you're looking at. R sub x, R sub y, R sub z is this R bar. And f sub x, f sub y, f sub z is the scalar for our force vector. And these are the scalar components for our position vector R. If you're calculating your calculator, you can enter this in calculator, or you can do this manually. And I'll do all my examples manually. And basically what you're doing is for the I, cross the vertical out, horizontal here, and then what we're going to end up with is a 2 by 2 ry f sub z minus rz f sub y. That'll be the I term. The j term vertically, we'll cross the j column, again cross this out, and then we end up with a 2 by 2. This term, this term, this term, this term. This will have a negative sign to begin with, so this will be minus rx fc. Okay, and then the whole term is going to be negative, and then rc minus fx, and then for k you cross the k column, this, and then we have this 2 by 2 here to solve. We'll go through some examples and do this. And the resultant moment of a system of forces, if you have a system of forces, it's just a summation of these cross products. So as you would do sum of forces, if you have a system of moments, you add the moments individually and come up with the total moment that you're going to be looking at. What I want to show you is a theorem that allows us to actually work these problems. Called Vernon's theorem. He lived from 1654 to 1722. And if you look back at when the fundamental laws that we use in engineering statics, when they were developed hundreds and hundreds of years ago. So this is not a new science. This is a relatively old science, hundreds of years old. And if you just go back in history and look at the structures that were built, 800, 900 years ago, particularly in Europe, just amazing the structures that were built. If you look at the pyramids in Egypt, thousands of years ago, it would be hard to replicate today the accuracy with which those were built, and yet there is no modern equipment. and they had to move all those stones, okay, manually with the help of some machines that they were able to use. Real crude, but it's basically, this is not a new science. So when you see textbooks, this is the 15th edition of Hibbler's book. Basically, there's nothing new in terms of the science. It's all the same. What's new are the problems and the presentation matter, but I guess. So Vernon's theorem. Let me go back to, let me just show you a problem. Show that first thing that I drew as an example, the previous sheet. So if I used moment is equal to force times distance, and I had this configuration cantilever beam with this force at an angle. In order to do that, what I would have to do is project that line of action and come out so I can calculate or define a perpendicular distance, d. There is no way, given how this would be described with x and y distances, there's no way I'm going to calculate that. Okay, you just can't do it. So for practical purposes, this doesn't work in terms of moment. But here's what Vernon's theorem says. The moment of a force about a point, in this case, this support A, okay, is equal to some of the components, moments of those components, and some of the moments of its components about the point. Without this theorem, we couldn't solve a basic statics problem, which this is a basic statics problem. So what this says is, and we sort of did this in the opening, I can define a y component. Of course, I'm going to have an angle when we do this, and an x component. I can now define the moment about A. The f sub x passes through A, so there's no moment arm. So the f sub x is not going to contribute any moment. The only moment contributed to A is this y component. And once I determine this y component, okay, which is going to be a sine function of theta times the magnitude of f, we know this distance. Okay, this is engineering structural, and we're going to give dimensions on x, y dimensions in our two-dimensional space. Three-dimensional will have the z dimension. Okay, so that's going to be real simple. So the moment here is just going to be force in the y direction component times this distance, and we'll call this distance x. Okay, so this distance is x, which we'll know and that's the total moment about this point. It would be the same if we took the magnitude of F and this distance D, perpendicular distance. This times this is equal to this times this. Okay. So the moment F times the perpendicular distance D is equal to the moment F sub y times the distance x about this support A. That's what Bernoulli's theorem says. It's very simple, but it's a powerful tool that lets us solve our statics problems. And then ultimately some problems in strength of materials, the second course in the sequence. Okay. So let's take a look at some example problems. These problems are in Canvas. On a heading for example problems, so we'll just take a look at it this way. Actually, now this a little bit better through here. Let me do it this way. Actually, copy the. We just do it this way. So this is the first example problem that we have. We have a gate. It's hinged here at C, so the gate's going to rotate in one of two directions around C. We have two boys that are going to push on the gate. F sub A pushes with a force of 30 pounds. F sub B pushes with a force of 50 pounds. And what the question asks is what direction will the gate rotate? A very, very simple problem. So all we need to do is just calculate the moments. This angle is 60 degrees, and this is a, I don't know if you can see it or not, this is a, yeah, this is a 3, 4, 5 slope that we have. I'm not going to draw the free body diagram. Well, okay, let's just show you the free body diagram if we're going to do that. All I would do there's my gate. This is the force at A. This is 30 pounds. Yeah, even for this simple problem, it makes it a little bit clearer just to draw the free body diagram. You'll see everything else, we definitely will draw a free body diagram. It says 3, 4, 5 slope. And then over here, this is 50 pounds. And the angle here is 60 degrees. And this is point C. So what we're going to do is calculate the moment. We know the x components. This would be the x component for the 30-pound force, the x component for the 50-pound force will pass through C. There's no moment created by the X component, so it's just the Y component that we're looking for. So this is FA sub Y. And this is FB sub Y. FA sub Y using slopes is 3/5. Okay, so FA sub Y is 3/5 of 30. FB sub Y over here this is the 60-degree angle, okay, and it's opposite, so it's a sine function is going to be equal to the 50 pounds times the sine of 60. The moment arm, 6 feet. And then it's an additional 3 feet from here. And so this is an additional 3 feet here. So the total distance out to the F sub A is going to be 6 plus 3 or 9 feet. So very simply, all I need to do is do the moment. So I'm going to about C for this first force. So this is 3/5 of 30 times the moment arm, which is going to be the 6 feet plus the 3 feet times 9 feet. And that'll be 162 pound-feet. Rotation. All I want to know the direction, so we're not adding anything together. It won't be an equilibrium. Rotation then is going to be clockwise this way. For this other force, F sub Y, or the other force then, it's the 50 pounds sine theta, which is 60 degrees. So this will be 50 sine of 60 times its moment arm, which is going to be the 6 feet. And this is 260 pound-feet. And this rotation then, when you look at this as it's pushing this way, rotation then is going to be counterclockwise. Okay, this way. This one is clockwise. This is going to be counterclockwise. So it's going to be 260 pound-feet counterclockwise. This is clockwise. So the rotation then is going to be counterclockwise. Okay. Two other things you can do with this problem. You could keep one of the forces known. You could say, find the other force that it had to push where this gate doesn't move at all. Okay, so you'd have one unknown. You could also change an angle or a slope. Say it might be easier just to change an angle. Find an angle that would keep this in equilibrium. Okay. So you can do an angle or you could do a force, choose either force, and so you can make a couple of different problems out of this. In that case, you would sum moments equal to 0 to solve for your unknown as you go through that. Okay. Here is second problem. Quite a bit more complicated, I would say. And we'll go ahead and describe this and go through the calculations as we do this. Okay, so what we have here is a crane, and this crane is supported. There's a tower, the crane tower AB. There are two jibs. Okay, there's a jib to the left of B, and there's a jib to the right of B. This is the lift cable system here, and this is the load that's to be lifted, and this load is lifted at a constant velocity. If there was a velocity on this, it would change the whole situation, change the whole dynamic loading on the system, and so you'd have to be real careful, make sure that you have a velocity that's going to be constant as you're going through this. So this ends up being a complicated, this is a pretty good example of what happens when you don't use a free body diagram. It makes it complicated to see what you need to do. And quite frankly, looking at that, I couldn't solve it unless I had a free body diagram. So I want to translate this to a free body diagram. So let's talk about how this is working. So the way this crane works is you have a load system over here. You're positioning a load, you're lifting a load. You want to take it somewhere on a structure. And over here, there's a counterweight such that you don't want this crane to tip. And the tipping would occur about this point A down here. Okay, this is point A. So you don't want this crane to tip. And it's going to tip because of an unbalanced moment. So what happens is the moments created this way must equal the moment created this way. So we want to sum moments equal to 0. And the problem, I'm just going to put the loadings on here. It's given the loadings, and we'll talk about this. The problem is all the loadings are given in megagrams, and we're going to convert to kilograms, and then because it's easier to calculate the math, and we'll convert back to megagrams. The question is, what mass do we need over here at C to counterbalance the load and the mass of the crane, basically the weight of the load and the weight of the crane? Okay. And there'll be a weight over here of that part of the crane system. And then what we want to find is C, and we have all the dimensions given. This is my free body diagram. Much simpler than this picture that we have up here. Okay. So here is the portion, the two jibs meeting at B. By the way, you all know how to get up to this cab. You got to climb steps, stairs. And if that's a, 50 foot crane, that's a pretty interesting climb, 60 feet, 60, 70 feet. It's a pretty interesting climb. So the unknown, or the unknown we have is C out here at the end. The load is 2 megagrams out here, and it's 12.5 meters from point B, and I'm going to explain this in just a second. G1 is the weight or the mass of this jib BD. So this is jib BD. It has a mass of 1.5 megagrams. And this is located 9.5 meters from B. G2 is the mass of this jib BC, and it's 0.5 megagrams. It's located 4 meters from B. And this point C is 7.5 meters. And let me put this down here. 7.5 meters. From C to B, so 7.5 meters. If you notice, I didn't show point A, and I didn't show 23 meters. The rotation is going to occur here. We don't want it to rotate here. But if you take a look, B is directly above A. Obviously, it's just the tower. The moment arms would be the same as if we took moments about here. So all of these loads, this horizontal distance is the same as if we looked at B, and basically the rotation is about B, even though, okay, so we don't need to show A, we just need to show B. These distances are the same here, and if you took moments about A down here, they would be the same. And so all we do is we just take moments about A, these two loads in a clockwise direction, this load in a counterclockwise direction, and the unknown load in a counterclockwise direction, and we can solve for C. So let's see if I can do this right over here. So some of the moments about B then. Unknown is going to be the C that we have over here. And this distance is 7.5. So I'm going to call, well, they're looking for weight, but we're going to work with mass. They want mass. We don't need to put the weight and convert back. The constant's the same. So the mass at C, which is going to be our unknown that we're looking at, times its moment arm, and its moment arm is 7.5 meters. Right here, 7.5 meters. And again, this is counterclockwise, so that's plus. And then we have the 5/10 megagram, and that's at a distance of 4 meters. That's in the see, we got the 7.5, so we have the 4 meters. That's 0.5. I wrote it, make sure I wrote it. That's the 0.5. Megagrams times its distance is going to be 7.5. It's going to be 4 meters up here. Sorry, 7.5. So that's 4 meters. And then we have 0.5 megagrams. That's 15 megagrams. And that's going to be in the negative direction. So this minus 15 megagrams times 9.5. And then this is 2 megagrams out here. 2 megagrams times the 12.5. That's minus also. And that's going to be equal to 0. Basically, when you add all these together, I'll come back over here. We end up with mass of C, and is going to be equal to 4.97 megagrams. It's a matter of taking moments. Again, you go from something that's like this to something like this, which allows you to solve. You can't see the forces. You have to be able to visualize the forces and how the forces work in here. Now, this is a problem. Basically, it's an example of taking a complicated structure, simplifying it into a free body diagram, and then you can add and subtract to get unknown force, usually taking moments. Okay, and again, it's the critical thing is the moments about this diagram. You wouldn't see a problem like this on the exam. I'm introducing this as a way to take a look at the free body diagram. That's actually the key, is the free body diagram that we're looking at. Okay. Take a look at three-dimensional problem. Actually, we're going to look at two three-dimensional problems. So what we have is a beam in three-dimensional space. X-axis, Y-axis, Z-axis. This is the beam. There's a force acting on this beam. And this force, you can write this as a Cartesian vector, that this is going to be a known quantity. Okay, so this is given to us. It's 600 I plus 300 J plus 600 K newtons. Okay, so that's the magnitude of this force F. It's acting at point B. What we want is the moment this force creates about point A. Okay, and if this is the front of the beam, this is the back of the beam. So this force is acting at this corner in the front. Point A is in the back of this beam, directed along this Z-axis. So this is A, this is B, and it's going to create a moment about A, and we want to determine what that moment is. Okay, so the problem says, what is the moment of the force F about point A? What we're going to do is use what we talked about, this dot product unit vector, the R cross F term. Okay. That ends up being matrix again. We're in an IJK axis system. So I'm going to call this MA, and this will be a scalar quantity. Okay, this is a scalar quantity. So the top row is this unit vector. It's in three-dimensional space, so this is going to be the IJK unit vectors. The second row that we're talking about is going to be the position vector. Okay, and so we need the X, I or I component, the Y or J component, and the K, Z component that we're looking at. Okay, so again, the dimensions correspond. So for the X component will be dimensions in the X direction. In the Y component will be dimensions in the Y direction, and Z component be dimensions in the Z direction that we're looking at. So the I component is this 2/10. We're going about A, so we're looking at the position vector F to A. And so I don't know if you can, yeah, you can see it clearer than what I can see it on what I'm looking at. It's 2/10 of a meter, which would be 2/10 of a meter from the back to the front. Okay, so it's 2/10. The J component which is the Y direction, is going to be the 1.2 meters. And for the K component, it's 0. A and B are both on the same plane. They're on the top of the beam. So this is the same plane. So there's no K component, it's a 0. And then the third row is just the Cartesian vector, the ijk component. So this is 600 plus 300 plus the third, which is 600. See, I'm going to change this to minus, I'm going to change this to minus 600 up here. Make that minus 600 in this direction. And we want the moment of the force about A. So for the I component, I'm going to cross this out. Have this this 2 by 2 by 2. Okay. So I have the point 2. See if I can get all this in here. So the 0.2 times 300 What's this out with 1.2 times 600? 0.2 times minus 600. I 0.2 times 600 minus, this is 0 times that, so that's a 0 term, so it's just minus 1.2 times minus 600 I. The J component, this has a plus sign, this has a minus sign, this is a plus sign. So the J component then is going to be minus, so it's going to be the 0.2 for the J component times minus 600, and that's all minus to begin with. Okay, so it's 0.2 times minus 600. J. This is 0, so that's what we have there. Last term, cross out here, we have this. So this is plus. We have the 2/10 times 300. And then minus 1.2 times the 600. Okay. And so this gives us 720I plus 120J minus 660K Newton meters. It's equal to MA. Using force, Cartesian vector, position vector, this equation here, times the unit vector. And again, we're in the IJK axis system, unit vector. It's not a specific axis we're looking at or a line in space, which would be different. We'd have to get the unit vector for that line in space. But in general, then it's just the IJK components that we're looking at. This position. Okay. This is definitely an older car. Hood is up. I don't know when they quit making these. The older cars, there was a rod that fit down right underneath the hood here for the engine block. And to hold your hood up, you have to push the hood up and bring that rod out, and then stick that rod. It could be a place where you could put the end of the rod in here, and that would hold the hood up. So there's a force being, in this case, being directed along this AB situation that we had. Okay. So what we want to do there's a force in the rod of AB. The force in AB is equal to 24 pounds. Okay, here's A to B. And what we want is the moment about the y-axis. And the y-axis basically is that hinge for the hood. So the hood is going to rotate around that hinge. There's going to be a moment created about this axis, which is the y-axis. Okay, so the problem says if we have a force of 24 pounds, what's the moment about this y-axis? So what we need to do is go back to the problem that we just took a look at, that says we want to use that 3x3. The moment then is about any particular point that we're looking at is going to be equal to the unit vector dot product with the R cross F. And if you notice, the F is obviously a Cartesian vector. So the first thing we need to do is find the Cartesian vector F. And since it's not at the axis or the origin of these axis systems, we can't, there's no dimension we can do to get that. Usually it'd be the X, Y, Z components. Okay, if it's all referenced from here. It's not now. The 2 points are out in space somewhere. So what I'm going to do is just get the coordinates. So for point A down here, and it's going to be sort of hard to see this. Here's the x-axis, here's the y-axis, and the z-axis. So I'm going to find dimension along here that's going to go to get the coordinates at this point from the origin. And what I find out here is there is a dimension out here. It's 4 feet. It's sort of hard to see. Okay, so it's 4 feet this way, which is that 4 feet this way. So that dimension that we're looking at in here is going to be 400. It's along the x-axis, so there's no y component, there's no z component, and the only component it has is 4. It's this dimension out here that measures that 4. So that's the coordinates for A. And then for B, this is B up here. I can do the same thing. I can find the coordinates for B. The X, again, you can find point B drops down to here. Here to here is B. And along the x-axis, there's a 2-foot dimension this way. Okay, so it's 2 feet here. And in the y dimension for B is also going to be 2 feet. So here is 2 feet out to here. B is dropped down to this point. And then from the origin this way is 2 feet. So it is 2, 2, and the z dimension, I think we can see pretty clearly, is this 4 feet here. So this dimension from B is 4. So it's a 2, 2, 4. This one is 4, 0, 0. Okay. So the unit vector, then we're going to just do the subtractions. Okay. B minus A, and we'll do that as we write our Cartesian vector. So F, Cartesian vector, is equal to the magnitude, which is going to be 24 pounds, times a unit vector. So the x component is going to be 2 minus 4. So it's minus 2i. Second component then is going to be 2 minus 0. It's 2, so it's plus 2j. And then we have 4 minus 0, which is plus 4k. And then we just take the square root minus 2 squared plus 2 squared plus 4 squared. And we're going to multiply this by 24, all these terms. And so I get Cartesian vector. When I do that multiplication, it comes out minus 9.80 I plus 9.80 j plus 19.6 k, and that's pounds. Position vector. So we're taking the moment. What we want is the moment about the y-axis. So the position vector is anything from anywhere along that Cartesian vector to the y-axis. So it's any vector that we can come up with. We may as well come up with one that's the easiest one to look at. And the easiest one for the position. Okay, here's A, so we can go A anywhere out here like this. Well, we already have this one dimension. It's along the A is along the axis. So why don't we go from here to the origin? This distance here that touches the y-axis makes it real simple. That dimension is 4. Okay, so the position vector then that we're going to look at then is just going to be 4. And since this is where we want the moment to be taken, it's from here to here, so it's plus 4. Okay, so 4i position vector, and that's in meters. So the moment about the y-axis is equal to unit vector y dot r cross f. So I'm going to bring this up a little bit further. So the m sub y okay. We had the ijk was in space is a unit vector. Now we're very specifically saying the y-axis only. Okay. So I have 0, 1, 0. It's about the y-axis, unit vector about the y-axis. This is designating the y-axis, quantity 1. Position vector is the 4, 0, 0. And the Cartesian vector is what we have here, minus 9.8 plus 9.80 plus 19.6. When I do this, it's all we have are zeros. Okay. So 0, 0, that's out. And then if I go here, okay, here, we'll get something. If I go to the K, it's 0 also. Okay, we're multiplying it by 0. So I'm going to just go here. And that's plus, minus, plus term. So this is going to be negative to begin with. And I got 4 times 19.6. J. And then this is 0 here, so there's nothing there. So all we have is 4 times 19.6 J. And this is equal to 78.4 J. And so what I'm going to say then is that the moment about the y-axis. Again, that's not had a minus sign in front of it, is equal to minus 78.4 J pound feet. So that's the moment created by this strut. Force .4 pounds in here. The moment about this y-axis then is 78.4 pound-feet. And I think we'll stop there for today. I've got one more item that we want to talk about, basically a force couple system, couples that we'll deal with, and we'll start on the next chapter also. The exam is a week from Wednesday. Okay, so this coming was a week from this coming Wednesday. And so on Wednesday lecture, we'll finish this chapter and start on the next chapter, chapter 5, which is rigid body equilibrium.